Good noontide and aloha from breezy, sunny Honolulu. This is Howard Wigg with the Hawaii State Energy Office. Welcome to you all. Welcome to Comfort, Health, and Air Quality. Now, wait a minute. This is about energy efficiency. That's not in the title. Well, turns out that any homeowner will first put the priority on comfort and health in their home. So we must establish that as the foundation. Then we can build on top of that energy efficiency. And that is what this program is all about today, that grand triumvirate of those three qualities. And we will demonstrate that putting all three together is easy and cost effective. And we actually give thanks to Mr. Putin and his vicious war because, among other effects, it has shocked the world oil price system, and it has shocked them in an upward direction so that when we are buying gasoline, paying for electricity, those prices go up and the price of everything else goes up. Thank you, Mr. Putin. But this gives us incentive all the more to leapfrog from our current level of energy efficiency to a whole new, much more efficient level so that we decrease our dependence on oil, because Hawaii's electricity is largely oil fired. All the more incentive. And this war that we have is going to continue for a while. And again, it's our wake-up call. The other part of the news is that when this settles, there may well be down the road another oil shock. Note that the other suppliers of international oil, when President Biden and other world leaders asked them to open up the spigots a bit to supply more oil to depress the price a bit, they said, no, not going to do it. So not much aloha for us and the other democratic countries. So the sooner we get to energy self-sufficiency, the better. And the basic, most obvious, quickest method of doing that is through energy efficiency. Now, before we begin, how in the world did we get funded to do these three seminars that we are doing? We did that through Ms. Sumi Han, the Executive Director of the Smart Energy Design Assistance Center and the Omanos Reis, and the power behind the throne for this whole operation. So, Sumi, descend from your throne and give us a bit of a welcome.
Thank you, Howard, and thank you for the promotion that I didn't get. So I'm not an executive director, but I am the assistant director of operations at the Smart Energy Design Assistance Center at the University of Illinois. So thank you so much for the warm welcome, and thank you everyone to attend today's webinar, and thank you for giving me a chance to briefly introduce our program, Building Energy Education Fundamentals. This program has two main goals. One is to provide education on fundamentals in energy efficiency and energy code. And then second, raise awareness in career paths in energy efficiency and code professions. Next, please. So this is our program webpage. If you haven't, please come and visit our program webpage. It has a lot of information that you will find it useful. And today, briefly, I want to talk about two main things. One is the instructor toolkit, how to use our curriculum. And the second one is access to our modules and how you can access it and how you can navigate our Moodle site. Next, please. So if you click instructor toolkit from our program page, it will give you some background information about our program and about how to use our curriculum. About our program, something like what is this training program about? Who should use this program? Why all focus on energy code? Answers to those questions, you can find it under about our program. And questions such as like, how should I select which curriculum to use, or how do my students and how can I access this modules? You can find answers under using our curriculum. And on the right, you see some videos. So we have some set of videos for the quick overview for different modules. So we highly recommend that you come to our website and click Instructor Toolkit, especially if you are our instructor or somebody who is teaching energy efficiency and energy code to your colleague or your students. Next, please. And then lastly, if you click access our modules, you will come to this Moodle site. And this is a free resources. So if you have not signed up for Moodle yet, we highly recommend that you do it as soon as possible to take advantage of resources that we developed and provide feedback to us. And by attending today's training, you have an opportunity to see what kind of materials are available in our curriculum and how it is utilized, because Eric has developed the training material for today based on our Moodle curriculum. So thank you again for giving us the opportunity to talk about our program, and take it away from here, Howard.
Hey, thank you so much, Sumi. Now to logistics. About half of you are architects, and here is your standard architectural language. Next slide. And here is the standard architectural description of the program. And here is what you will learn. And just to follow up on Sumi's presentation, those Moodles are really, really terrific. If you are educators, and we have several educators in the audience today, by all means, follow up on them. And here's our cast of characters, presenters, and it takes a team to make a village or make a webinar. And for Karen, Gail, Kira, Ellen, Elena, thank you so much. They are busy working even as we speak. Next slide. And here, you see, last week we had the education fundamentals and energy code basics. Next week, we have Beyond Code Zero Net Energy, and I need to point out that each new iteration of energy codes gets more and more and more efficient, and our goal, national goal, is by 2030, all homes, new and all buildings shall be zero net energy. So this next week's program will put you on that way. And then finally, Sumi's organization is doing a Train the Trainer workshop on the 29th, and especially for educators. This is a must go to event. Next slide, please. And this brings us to Mr. Eric Kolderup, who has been Hawaii's energy consultant and presenter since before some of your parents even met one another. Our first residential code, thanks to Eric, came out in 1994, and he has been with us periodically ever since. So he knows just a wee bit about Hawaii's climate and Hawaii's energy code. So please take it away, Eric.
All right, well, thank you, Howard. And yeah, welcome to everybody who attended last week's webinar, and also welcome to those of you who are new this week. So today's topics are going to address issues of primarily indoor air quality, thermal comfort, and energy efficiency. And as this diagram tries to imply, these are related topics. The indoor air quality strategy that we choose can affect the thermal comfort and vice versa. And of course, both can have a big impact on energy consumption. For example, do we get comfort with natural ventilation, or do we use air conditioning, or perhaps both? And of course, the choice of how we deliver that comfort clearly affects air quality and energy consumption. So I'll talk first about indoor air quality and then thermal comfort. And then we'll cover a few important air conditioning issues, so system sizing and duct design and installation. And then Justin Beiser from Hawaii Energy is going to talk about energy efficient water heating. And finally, I'll talk a little bit about lighting. And then the important part is that if you make it through to the end, you will be eligible to be selected for one of a few Zippy's gift cards. Clearly the most important part of the day. So indoor air quality. We're going to give a quick tour of the education modules that are available from that BEE fundamental site that Sumi described. So we're going to talk about the first two, the fundamentals of indoor air quality, and then the fundamentals of building ventilation. And I encourage you to check out the online materials for more details if there is a element that you're especially interested in. Plus, we've added a little bit of material about VOG, or volcanic smog, and also COVID-19, because VOG is obviously a very important issue in Hawaii, and COVID-19 is, of course, a timely issue related to indoor air quality. So I hope that sounds all right. So first, the fundamentals of IAQ. It's important, maybe it's obvious, because we do spend a lot of time indoors, and because indoor air quality is often worse than outdoor air quality. So there's several factors you see there on the left. There's the outdoor environment, so what is in the air outdoors, which building materials you choose, how tight your envelope is, and what the rate of air exchange with the outdoors is, what kind of ventilation you provide, and then of course what the occupants do in the space, what kind of stuff they bring in, whether they bathe regularly or whatever. So there's a lot of factors affecting IAQ. And I think it's kind of a wonder we're all still breathing, considering all the stuff that's out there to get us. There are chemical pollutants, which can include CO2 you're exhaling, if the concentration is high enough. And then there are, of course, lots of sources of dusts and particulates, and there are microorganisms, some of which are harmful to us. So these are all factors to consider in IAQ. Now, particulates come from furnishings and building materials. They can come from our carpet, our clothing, furniture, the insulation materials that we use. Dust can come from skin cells, so stuff that falls off of us, or then things that we track in or that come in through cracks in the walls or open windows or whatever. So there's lots of sources of particulates, of course. And then sources of chemical contaminants. Our building materials can be sources of chemical pollutants, right, via off-gassing. So the glues or paints, those kinds of things that we use, the wood even, and some of the, the building board materials will off-gas things such as formaldehyde. And then the insulation materials we use may also off-gas VOCs. There are environmental contaminants, so that's stuff that's maybe coming in from outside, so ozone from the outdoor atmosphere. Radon's not really a problem in Hawaii. It's more of a problem in the continental US. Maybe wildfire smoke. It certainly is a problem in California. And of course, cigarette smoke can be a particulate problem. And then the cleaning products that we bring in can also affect our indoor air quality. So what do we do about these chemical pollution sources? And I guess just to backtrack, I'll say that, there is no one solution to indoor air quality. There's sort of a set of strategies that we need to employ. And if we have combustion appliances, like say a kitchen range, properly venting that will help significantly. We can also select low VOC building products. So there are databases out there that'll help you identify those. More and more of those are available all the time. Like I said, radon's not that big an issue. Of course, avoiding indoor smoking is an issue or important strategy. And then there's controlling moisture levels. So moisture in itself is not really a pollutant, but high moisture levels can cause materials to degrade and can also lead to mold growth. So that can lead to pollution problems. And then, in Hawaii, warm, humid air can cause problems when it's leaking into an air-conditioned building. So that moisture can cause condensation. The moisture can condense out of the air on a cool surface if it's the inside of the building's air conditioned. And that, of course, can lead to mold and water damage. So we really need to pay attention to air leaks. So the illustration here is showing that moisture vapor does travel through building materials through diffusion, but that's a tiny amount relative to what gets transferred through a little crack in the wall or a little small opening if that warm, humid air is traveling through that crack. So we need to pay attention to leaks and where they occur in order to avoid some of these potential moisture and mold problems. And then when we consider indoor conditions, humidity or relative humidity can be important. And there's some evidence now that there's kind of a sweet spot for indoor relative humidity that's between about 30% and 60% that's optimal for human health. Now in Hawaii's climate, it's the higher end of the range that we're usually paying attention to. Above 60% relative humidity, the chance increases for mold growth and dust mites, and bacteria and viruses seem to live longer or survive longer in the air at higher humidity levels. There's kind of that sweet spot where they don't last as long. And there's, again, the dry side under 30% relative humidity is not really that big an issue in Hawaii in most buildings, but you might encounter that in an airplane or whatever. And there's evidence that our defense systems, our mucous membranes dry out and we're not as resistant to things like airborne viruses when it's dry. So that's why we try and target that middle range if we can. And as I'm sure some of you are aware, we've been making buildings tighter and tighter over the years to save energy and avoid infiltration. But that helps reduce some potential air quality problems, like maybe mold growth within the walls due to leakage. But it also reduces the dilution of indoor pollutants. So we're not getting as much outdoor air. So we solve one problem and create another, as we sometimes do. So the strategy and the approach basically required by the Energy Code is that we seal tight and ventilate right. So we seal the envelope to minimize air leaks or unwanted air leaks, and then we bring in outdoor air through some kind of ventilation system where we can filter it and remove outdoor pollutants. So we talked about particulates. And so why do we care about them? Well, there's, again, evidence that these have an impact, adverse impact on health. So the first big idea there is that particulates in indoor air have adverse effects on health. They can trigger asthma, they can be irritating, they can carry virus and bacteria. The second big idea is that the fine particles are even greater concern. So they get deeper in your lungs, and they may even affect your cardiovascular health. So I'm not an expert on this, but I think there's, from what I understand, quite a bit of evidence that we need to be concerned about these. A lot of you have heard of PM10 and PM2.5. So that's referring to the particle size, PM10 being 10 micron range and 2.5 being the 2.5 micron range, or millionths of a meter. And so those smaller particles have been shown to be able to enter the blood through the lungs. The image there on the right shows the size reference. So a human hair, 50 to 70 microns. So that PM10, is about, you fit about 5 of those on a strand of hair. And then the PM5, there's 4 times again as many of those. Very small things. So we'll talk a little bit more about mitigation measures for particulates. Well, when it comes to chemical contaminants and occupant health, there are some known detriments. For example, high CO2 concentration can cause cognitive function, or can affect our cognitive functions. Carbon monoxide, of course, can cause serious problems, and then other chemicals can cause asthma or respiratory problems. So both particulates and chemical contaminants are a concern. Now, We also added some material, as I mentioned, about VOG. So I think VOG is probably an air quality problem most people in Hawaii are aware of. It's, it's created when sulfur dioxide gas from an eruption reacts with the atmosphere and it converts into fine particles, which can be acidic. So if you're close to the eruption, you may be affected by both the gas and the particles. Those farther away, like on neighbor islands, are mostly affected by the particulates, which can be a health problem. So you see there the list of potential health effects from VOG. And there's a website link there which has a lot of good resources to find more about what VOG is and how you can mitigate it. If you're wondering if it's safe to go outside or whether you need to close the windows, you can check this really great Department of Health website. So it shows air quality measurements at several locations around the state. You can see that it lists the AQI levels or air quality index levels, green, yellow, and so on. There's a link on that website that gives you more information about that, what that means. So this is the table that describes that AQI scale. And this can help you figure out what levels might be a concern depending on your situation. If, for example, people with asthma would want to be more careful at lower levels. And there's this table also available from the website listed here, covers that same kind of information, but specifically for sulfur dioxide. So if you do live close to an eruption vent, you may want to pay attention to this and also check the monitoring stations. So yeah, so VOG is kind of a unique situation for Hawaii that we need to pay attention to. The other timely topic is COVID-19. And the idea here, there's no single solution to preventing the spread of COVID-19, just like there's no single solution to any or most indoor air quality problems. But we have several tools. So there's source control, which is up to the occupants. So we can, for example, wear a mask if you might be sick, or you can stay home, so isolate yourself. There's source removal, so we can use our systems to help filter the air and disinfect the air. And then there's dilution, which is ventilation. So there we're bringing in outdoor air to reduce the concentrations of infectious particles and reduce, hopefully, the rate or the chances of infection. So again, we haven't found any one strategy to mitigate COVID in buildings. The Smart Energy Design Assistance Center does have this nice website that gives resources on a number of building-related COVID mitigation topics. So I suggest you check that out. And for the engineers and nerds in the audience, maybe that's a redundant statement. I suggest checking out this white paper produced by the HVAC design firm Taylor Engineering, which is based in the Bay Area. They pull together a lot of relevant research on mitigation strategies in buildings. And the table on the left is a summary from the report of potential strategies with their effectiveness and rough costs. And then on the right, it shows estimates of infection probability and how it drops with increasing ventilation rates. The blue bars is when people are not wearing masks. The red bars when people do wear masks. So what it shows is that ventilation clearly makes a difference. So higher ventilation rates do help, but masks also help control the source and significantly affect probability of infection. So again, there's no one strategy, but some good information about where we might try to invest our resources. So I suggest you check that one out. Okay, so that's our quick tour of indoor air quality. So please check out the online modules for a little bit more information. Now, as I noted, one of the strategies for good indoor air quality is ventilation. So let's take a quick look at the fundamentals of building ventilation and some minimum ventilation standard information. Also, we've added a little bit on the Hawaii residential ventilation requirements. So if you've got an air-conditioned home, what are the ventilation requirements? And then a little bit on air purifiers, because that's one strategy to help improve indoor air quality as well. So uncontrolled infiltration and exfiltration can be a problem in many cases, especially in air-conditioned homes. So in Hawaii, it could lead to higher AC consumption and also potentially to mold and material degradation problems. But we do want some outdoor air entering the home, right? But the problem with relying on infiltration is that it's not controlled and it varies over time. And you may not be getting enough air at times, say when the windows are closed. So as noted earlier, a good strategy is to build tight and ventilate right. So try to control that unwanted exchange. Now, that said, natural ventilation can be a great strategy for providing comfort energy efficiently. And it can also provide ventilation for air quality, but there are some challenges and limitations, right? It might not be appropriate if it's noisy outside or the outside air is dirty. And if you use it together with air conditioning, you might be creating some humidity problems. So natural ventilation is a great thing to consider in Hawaii, and we'll talk a little bit more about it in a few minutes, but it's also something to you may not be able to rely on all the time. So the other path is mechanical ventilation, meaning use some type of fan-based system. So the big advantage is that you can provide a specific amount of air, and depending on the approach you use, you might be able to filter that air, which helps prevent bringing in particulates from outside. And you can control the ventilation to provide what you need and not waste energy by bringing in excess outdoor air that's uncontrolled. So there are some advantages to mechanical ventilation. And I'm going to spend a few minutes talking about residential mechanical ventilation options. If you're interested in commercial ventilation, there's more material in the online modules that I hope you'll check out. So on the next slides, I'll go through these 3 different strategies. The code for air-conditioned homes doesn't tell you which one to use. And we'll see shortly that the code specifies a minimum ventilation rate, but you have flexibility in how you actually deliver that ventilation. So the first strategy is probably the simplest and cheapest one, which is exhaust only. So here you use 1 or more exhaust fans, like the bath exhaust, kitchen range hood exhaust, or some other dedicated exhaust to draw air out of the home that causes indoor air pressure to be lower than outdoors. So outdoor air is sucked in through the cracks. So we don't know for sure where the air is coming in. So that's one drawback here. So like I said, maybe the simplest and cheapest approach, but the air may not be getting filtered. So that's a potential problem. And depending on where it comes in, that warm, humid air might cause moisture problems when it comes in contact with cool indoor surfaces, if this is an air-conditioned house. But this is one strategy. The second is called positive ventilation. So here a supply fan brings in air to the home and the home is pressurized, and then that air leaves through exfiltration or maybe still through bath fans or exhaust fans. But here again, now you're able to, well, this diagram here is showing the central air handler being the fan that's drawing in some outdoor air. And then there's a motorized damper that will close when the fan's not running so that you don't have extra air leakage. So compared to the negative pressure approach, this has the advantage that the air can be filtered. So you're filtering that outdoor air. So if you're concerned about the quality of outdoor air, then this is probably a little bit better approach if it's dirty air outside. And then finally, there's the balanced ventilation approach, which has both supply and exhaust fans. So this is potentially the best for indoor air quality because the air can be filtered and you can control where the air is leaving the home. So this advantage, or this example here, shows an ERV, which is an energy recovery ventilator. So that's a box basically that includes 2 fans and a heat exchanger. May or may not be, cost-effective thing to do in Hawaii, but there are a number of approaches to balanced pressure ventilation out there. And so how much air do we need? ASHRAE publishes 2 standards. 62.1 covers commercial ventilation and 62.2 is the residential version. I'm not going to go into details about these. I'm going to talk about the Hawaii Code in a second. But both of these standards, when you calculate the amount of ventilation air, you sort of consider two things. First, there's the area of the space. So you have a certain amount of air based on the size of the space. And then there's sort of the person-based rate. So you have a certain amount of air based on the number of people in the space. The idea is that, you know, the space and all its surfaces and such are responsible for some of the pollution. And then the people in the space are responsible for some of the pollution, especially CO2. And so you consider both of those things when you calculate the amount of air you need. But for low-rise residential buildings in Hawaii, the energy code, the IECC, points to the IRC, International Residential Code. So the energy code doesn't specify a ventilation rate, but it says you should have ventilation according to the IRC. The equation here shows you the how you calculate that rate in cubic feet per minute. And it's obviously depends on the floor area and the number of bedrooms. That's the continuous ventilation rate. So that's what you would supply if the fan was running all the time. The code does allow you to run the fan as little as, say, 15 minutes out of every hour, but then you need to provide more air when you do that, or basically 4 times the rate. Or if, say, you run it every 20 minutes out of the hour, or 20 minutes out of the hour, you'd need to apply 3 times the continuous ventilation rate. I should note that ventilation is not required for homes that follow the tropical zone energy code compliance path, which we talked briefly about in last week's webinar. And if you don't like equations, there's also a table. So for example, if you've got a home that's 1,500 to 3,000 square feet with 4 or 5 bedrooms, then the minimum ventilation rate would be 75 CFM. And if you ran 15 minutes out of every hour, you'd have to provide 300 CFM for that 15 minutes. And once again, the choice, whether exhaust only, supply only, or balanced, is up to you. The important thing I'll point out, though, when you consider this, make sure you do some research into potential humidity issues. If you are bringing in warm, humid air to a home that's only intermittently air conditioned and is not being properly dehumidified, you can end up with moisture problems and mold in the house. So it's important to remember that. All right, and so to wrap up the topic of both air quality and ventilation, we wanted to mention air purifiers or air cleaners. These are devices that you may be familiar with that are designed to filter the air in a single room. And most of them have high efficiency filters that remove small particulates from the air. Some of them also have filters that remove gases from the air, which can reduce odors or absorb other pollutants. And if you're choosing one, it's good to know about the performance metrics. So there's the clean air delivery rate, which is an indication of how good a job, or basically how much clean air that it delivers. And then there's the energy efficiency rating, which is the CADR per watt. So how much fan energy does it need to deliver that air? And the higher the number, the better there. And these can help with VOG. So if you're close to the source, then you may want to make sure you get one that filters both particulates and gas. Otherwise, a filter that just deals with particulates can be effective to remove those particulates that are in the VOG. So how do you choose one? Well, the US EPA has this guidance about choosing the right air purifier size. So based on your room area, what minimum clean air delivery rate should you choose? And the EPA also has on their Energy Star website a listing of filters that meet minimum energy efficiency targets. So there are specs there on the efficiency ratings, and you can browse through there. So I suggest looking at that if you're in the market for an air purifier. All right. So I know this is kind of a quick tour, or maybe not quick enough for some of you, but sort of a quick tour of the IAQ and ventilation. And as I've said a few times, I encourage you to check out the website at the Smart Energy Design Assistance Center for more details on each of those modules. So we're going to get into some of those BEE fundamental materials related to air conditioning systems in a few minutes, but we've added some discussion here of thermal comfort strategies because in Hawaii, air conditioning isn't necessarily the only option to providing thermal comfort, as I think we're all probably aware. Now, there is some science to thermal comfort. So it's a function of heat balance. You want the heat generated within your body to be equal to the heat loss from your body. Otherwise, if you're generating more heat than you're losing, you're going to feel overheated. Or if you're losing more heat than you're generating, you're going to feel cold. The amount of heat you're generating, of course, depends on your activity level, whether you're walking or sitting or running. And then it also varies a little bit by gender and age. The heat loss is affected, of course, by your clothing, how much clothing you're wearing, but it's also affected by these environmental factors like air temperature, relative humidity, air velocity, and what we call mean radiant temperature. That's the average temperature of all the surfaces surrounding you, the ceiling and the walls and the floors. If those are hot, then your body is losing less heat and you need a colder air temperature to feel equally comfortable. So it's a function of heat balance and physics. So all these factors affect heat loss from the body. So in our buildings, we can look for combinations that provide good comfort. So it's not necessarily just air quality that we have in our tool belt, so to speak. We can choose a strategy to provide the comfort as efficiently as possible. I'm sure a lot of you are familiar with the concept of a comfort zone. So this is a range of temperature and humidity at which most people feel comfortable. And so on the x-axis, you see temperature, and then going up and down, you have increasing levels of humidity. So this comfort zone will shift to the left if you have more radiant heat. So like if you're out in the sun, you need cooler air to feel equally comfortable, right? Or it shifts to the right with air movement. So if it's windy, then you need warmer air to feel equally comfortable. So these give us tools to think about when it comes to providing comfort. And of course, if you add or remove clothing, or you're more active or less active, this comfort zone moves. So what are the boundaries of this comfort zone, you may be asking now? Well, the Center for the Built Environment at UC Berkeley has this great online tool, they call it the Comfort Tool, that allows you to enter different conditions and see the likelihood that people will be comfortable. So you can enter, for example, the air temperature, mean radiant temperature, the airspeed here in feet per minute, and play around with that and then see where those conditions fall within the comfort range on the right. So, you might try and target being in the middle of that comfort range, which gives the greatest probability that people in the space will feel comfortable. So yeah, check that out. It's a very useful, interesting online tool. Now, if you want to use air movement, you can use ceiling fans for that. There's different ways to get air movement into space, but of course, ceiling fans are a great one. And if you play around with that comfort tool, you'll find that as you increase the airspeed, for example, this is the airspeed in feet per minute. If you go from 0 up to say 100 feet per minute, which is a good target for ceiling fan, then the cooling effect of that is about 4 degrees. So that means you can feel equally comfortable with temperature 4 degrees higher than if you didn't have that air movement. So this is something that can be really valuable as a strategy in Hawaii, of course. I also wanted to refer you to this great ceiling fan design guide, also created by CBE. And they also have another online tool, they call it the fan tool, which will help you design a ceiling fan system, figure out what size and how many fans you might need for your space. But the guide also includes some kind of general guidance. So on sort of the appropriate size and fan layout, So how big a fan do you need for a given space, or when do you need multiple fans in a space to provide, say, adequate coverage? There's also guidance about fan placement relative to ceilings and walls. So you see, in this case, say it's a 5-foot diameter fan, then 5 times 0.2 would be 1 foot. So they recommend you keep the fan at least 1 foot away from the ceiling to get good airflow. So there's a whole bunch more information in that guide. So I suggest checking that out. Now, ceiling fans are also, because they're such a great idea in Hawaii, they are required by the Hawaii Energy Code for residences. And in fact, you can provide a ceiling fan in a new building or a ceiling fan rough-in. So that means there's a junction box and wiring that allows the occupant to install the fan of their choice. But if you don't provide that, then it's very expensive for somebody to add a ceiling fan in a room that's not wired for it. So then we get to the thermal comfort strategies. So there are different ways to provide equal comfort according to the science, right, of heat loss. So we can provide 76-degree air in with an AC system. If we have a well-insulated ceiling, we might keep that ceiling a little cooler, so the mean radiant temperature will be lower, and people might be satisfied with a 78-degree set point. So you might save a little bit of AC energy. And then if you go to the next step and also provide air movement, you get that other 4 degrees of basic cooling effect. And you get by with 82-degree thermostat set point, which of course will save you a bit of AC energy and reduce the number of hours your AC needs to run. And then in many parts of the state, you could go all the way and get rid of the AC and just rely on natural ventilation and be comfortable up to, say, 82 to 84 degrees with some air movement. So all these would give you equal comfort. The one other point I want to make is that if you have a system that doesn't do very good with humidity control, maybe it's a really oversized AC or it's not working right, then at higher relative humidity, you need yet lower air temperatures to save energy or to feel comfortable. So that's a reason to make sure your system is doing good humidity control, or humidity control rather, so that you can stay comfortable at higher temperatures and need less AC energy. All right, so you're sold on natural ventilation, right, as a strategy. Is it feasible in your location? I'm going to show one more tool, online tool from this Center for the Built Environment. They call this the Klima tool. And it allows you to choose a location. They've got, I don't know, a couple thousand locations around the world, including a number in Hawaii. And they have typical year weather data, and you can plot it in a number of different ways, including on the right, where the white areas are hours above 84 degrees. So on the windward side, on Kaneohe Bay, you know, there aren't many hours a year when it gets over 84. On the leeward side, the Barbers Point weather station shows that there is a significant number of hours when it's probably going to be hard to maintain good comfort with natural ventilation, but there's still plenty of the year when it is feasible. So this helps you decide on an appropriate comfort strategy for your project. And then finally, on thermal comfort, here's another motivation to consider natural ventilation, or at least, you know, using natural ventilation part of the year. These are typical air conditioning costs in Hawaii. So anywhere from $800 to $2,000 a year, depending on the type of system. So that's a significant chunk of change, and can be reduced somewhat by integrating natural ventilation. All right. So hopefully that was a somewhat interesting tour of potential thermal comfort strategies. So now, you know, if you are planning an AC project, and many projects are using air conditioning these days, especially in the warmer parts of the islands, then system sizing is an important issue. So I wanted to touch on that briefly. There are some building energy education modules. We're going to talk first about this one on mechanical equipment sizing overview. There's plenty more details within these other manuals. So if this is a topic you're interested in, I encourage you to check those out. So this is Introduction to Mechanical Equipment Sizing. I mean, the basic idea is we want to choose an AC size that's big enough, but not too big, because there are a number of drawbacks to choosing an AC system that's bigger than necessary. Energy use, it can be less efficient. Comfort, it can be louder and provide less stable temperature control. The equipment life might not last as long because of potential short cycling, cycles on and off more frequently. It might not provide as good, do as good a job with dehumidification. An oversized system doesn't run as many hours. And so during those hours it's not running, it's not dehumidifying the space. There may also be, higher peak demand and of course higher first costs with a bigger system. So lots of reasons to consider putting a little time into selecting equipment size. Now, if you are the contractor or engineer who's doing this work, you would consider the climate, the envelope, and the building configuration to calculate maximum cooling load. And you would use that information to select the appropriate system size. So, is this really a problem? Well, there's plenty of information to say that, the typical rules of thumb that we use, like for example, 500 square feet per ton, is too conservative. These blue dots show actual cooling loads in buildings, in homes. The higher the number means basically the smaller the air conditioner, because it's a higher square feet of floor area per 1 ton of air conditioning. So this kind of indicates there's lost opportunity. So there's money been left on the table here in a lot of cases. If you're interested in more information about how to do this, the industry standard for residential load calculations is called Manual J. And then there's Manual S, which talks about equipment sizing based on those load calculations. So there's a lot more information in these online modules. But as I just said, so Manual J gives you the loads, and then Manual S tells you how to select an appropriate system size based on those loads. And so it can be worth spending a little extra time, because you might reduce first costs, might have lower energy costs, and so on. You might get better comfort, and you might have lower energy use and contribute to a more sustainable environment. So much benefit to right sizing your AC system. So let's pay some attention to it. And then the other topic I want to talk about is ducts. So if you have air conditioning system, you might have ducts, and these can have a big impact on the performance of the system. So I'm going to quickly touch on content in some of these modules that you see listed here. So duct design affects the energy efficiency and the cooling performance in sort of 2 ways. It affects the fan energy. So friction loss there. If you have high friction loss in your ducts, the fan needs to work harder to move the same amount of air. So that's not good. And then temperature and air loss. So if you have leaks in your ducts, or you have poorly insulated ducts that are absorbing heat from the attic, then you're losing a fair amount of your cooling. And that's an efficiency and performance problem. So there's been plenty of research that shows that ducts are a big source of inefficiency. You can find all sorts of horror stories of unconnected ducts or big holes in ducts, or ducts going in figure eights that restrict airflow. So it's worth paying some attention to your ducts. So when we talk about friction loss, there's the material we choose for ducts and the length of ducts. There's also the layout and the bends. We want to have minimum number of turns necessary. And then there's sizing. Larger ducts mean lower pressure loss. Smaller ducts, higher pressure loss. So we want to consider the appropriate size selection. And of course, on the air and temperature loss side, there's sealing, which is important to minimize air loss, and then there's insulation to minimize the thermal heat gain, especially if you're in a place like the attic. So briefly on friction loss. Friction loss in a duct is caused by turbulence, basically. So if you have rougher duct textures, like a flex duct, which is sort of rough on the inside, you get more friction loss. Also, if it's longer, the longer it is, the more friction loss. The more it bends, the more friction loss. So the bottom line is you want to make duct systems as short and straight as possible to minimize friction losses. And then duct fittings are all of those connections and bends in the system. They also cause turbulence and pressure loss. So we want to minimize the number of bends and changes in direction. Air likes to go straight. So pay attention to the fittings. That can make a big difference in how much airflow you get for the same amount of fan power. And then air and temperature loss. So one strategy that's becoming a little more common is to put your ducts in conditioned space. One way to do that is to insulate up under the roof, as you see there on the upper left side. Otherwise, if the ducts are in the attic, we know that the attic gets really hot. And not only did the ducts, lose some of that cooling to the attic, but if they're not insulated well, you might get condensation from that warm, humid air in contact with your cool duct. If not in conditioned space, the ducts need to be insulated, of course. And this gives some ideas of places where you might get leaks. It might not just be at duct connections, but it's where the boxes hook up, where the registers hook up to the drywall. There's all sorts of areas that we might find unexpected leaks. And sealing is important. So the energy code includes requirements about how ducts may be fastened and sealed. And there are a few different acceptable strategies. So we can use UL rated duct sealing tape. So there are some tapes that are considered acceptable, but standard duct tape that's not rated is not good because it'll dry out and fall off pretty quickly, especially in a hot attic. There's also other materials like paint on duct mastic or caulking or other sorts of sealants. But there are some code allowed and code not allowed methods, so make sure to pay attention to that. Lastly on ducts is duct pressure testing. So as I noted, duct leakage can be a significant issue, and it's hard to know how leaky the ducts are without testing them. So the energy code does require some testing for residential ducts. It sets a maximum leakage rate under certain types of test conditions. And on this next slide, here's an image of how that works. So you take basically a fan and you hook it up to the duct system. You seal all the other openings, like all the registers and grills, and then you turn the fan on and it sucks air out of the duct system. And of course, the leakier it is, the more air you'll get. So this tool uses the measurement of airflow together with the pressure to come up with an estimate of the leakiness of the ducts. So you do this test during construction. And if you don't meet the limit, then you do some hunting around to figure out where those leaks are. So here's a quick video that shows, gives a demonstration, shows you what some of this equipment looks like.
So we have set up here is a duct blaster test for pressurizing the ductwork. We've got our fan set up to blow into the furnace housing. The last thing we got to do for setup prep, now that we've verified all our vents are sealed in the house, is to pull the filter out of the filter slot so we get even depressurization in the ductwork. We've got our speed reference line hooked up to the fan, which is to our flow measuring controller and pressure measuring controller. And the other line is running out to a supply vent in the space to measure the pressure in the ductwork.
So as I noted, this duct testing is required in the IECC. So that's something that we should pay attention to if you're working on a new home design. Okay, so that's it for air conditioning. Now I want to introduce Justin Beiser from Hawaii Energy to talk about energy efficient water heating. So Justin is a program specialist with Hawaii Energy, and he's going to tell you about some energy efficient water heating technologies, as well as some example projects they've worked on.
All right. Well, thank you so much, Eric. And thank you everybody for being here today. And I always appreciate the opportunity to really discuss our programs and projects that the team gets to work on. So I am an affordability and accessibility program specialist. So what is affordability and accessibility programs? Next slide, please. So basically, these programs are community focused. They're on both new and existing buildings. On the screen, you can see an overview of the various programs that I either work on directly or indirectly. But all these efforts really are designed specifically for populations that Hawaii are either low income or they're hard to reach, or in other words, inaccessible for various reasons. And today my primary focus is really just on some of the existing buildings and heat pump water heating options that you may that may be available to you with a variance, as an example. And of course, Howard, Gail, Eric, may be able to elaborate on some of those topics that we're going to discuss as well for that. But I'm always happy to answer questions that you may have, so feel free to let me know. And then I'm also going to briefly discuss some of the HVAC and air quality programs that these we're able to offer these populations. Let's see, so, just looking at typical energy demand for Hawaii households, I think the programs that I help implement for these ANA communities, or affordability and accessibility, deal primarily in water heating at 40%, which you can see of the energy consumption, refrigerators, freezers at 50%, 15%, and I did discuss that briefly in a previous session, but I'm also going to just touch on some of the air conditioning options, which you can see is 12% of consumption. And I did speak briefly on that on new construction, but I'm going to elaborate a little bit more about our standard rebate options on these existing builds. So next slide, please. All right, so if we just take a quick look at water heating costs, especially compared to the rest of the country, what I've seen historically, Hawaii is the highest electric utility cost in the country, and we know that it's roughly 3 times the national average. This kind of gives you a basis here, 2.5 to 3 times. I've seen it pretty much 3 times. So next slide, please. All right, so I just wanted to show an example of basically a standard water heater versus the same size heat pump option. The costs you see on the screen, they're obviously going to vary because we import oil to Hawaii, which often fluctuates. And I think we've all seen that recently. But the thing to take away is really that the cost that you pay per kWh is going to go up or down over time. And the estimates you see on the screen are a little bit older. I think I've seen it go up at least 10% since this was done. But if you're looking at just the estimated costs, I think these are about 2.5% instead of, or 2.5 times versus 3 times. So at that, I'm sure you could do the calculation. Next slide, please. All right, so here's an example. So we saw that it was roughly 63%. So here is just an example that does not focus on the solar water heating option. Obviously, if you're new construction, you're looking at solar water heating. If you're existing build, you're doing a full rehab, or you're just looking to replace that electric resistant, this gives you an idea as to the costs you might incur for that. So if we look at a heat pump, in average cost as of now might be in the vicinity for an 80 gallon of about $2,400 without installation, versus what you might look at for a standard electric. It's no more than 2 times, 2.5 times tops, but you're looking at 63% more savings there. So we just want to make sure, if you are considering replacing, or one of your clients are, the other aspect is it's a reverse HVAC system or central AC. So often if you have the opportunity to put this in, say, a garage setting, it keeps your garage nice and cool for that. Next slide, please. So, when would you look at a heat pump as an option versus a solar for an existing build and a variant? So this is, one aspect of it. The sunlight exposure is a big part of how efficient the system's going to work. Additionally, we know that the cost of installing a heat pump is far less than the cost of a new solar water heating system. So this is something that you can expect to have your clean energy ally or solar contractor help you determine, what the efficiency would be based on the exposure to sunlight. Next slide, please. All right, so again, to determine the feasibility, there's also vegetation elements. So if it's feasible to cut down trees, either in your particular yard, but if it's not your property and it's not something that you can actually take down, that's another consideration. So that shading and limited sunshine, just based on where you're located in the surrounding properties. So we just want to make sure that anyone that is looking to upgrade their water heating system knows that there are other options, and that's what that variance would be applicable towards. Next slide, please. Okay, so again, where are some of these locations that are going to have limited light that really would be out of your control? Well, one is in particular valleys or areas where just the sun doesn't hit it the way it would be feasible to actually pay for that cost, because you do a cost assessment based on how much energy you can produce with the new solar thermal system. And again, that's something you want to discuss with your clean energy ally. But I mean, as far as areas on this island, we know we have a lot of climates throughout the state, but certainly just on this island alone, there's a big difference between living in Kaneohe and Waianae as far as your sunshine. And so there's just a lot of opportunities that we want you to consider. And Hawaii Energy is here to help you with either option as far as how you proceed. So, beyond any federal funding or grant or tax credit or any element that you're able to take advantage of, Hawaii Energy does offer some opportunities for you to look into it. I also have a lot of additional information on heat pump water heating systems, so feel free to give me a call or send me an email if you have any questions on that option for you. And next slide, I'll just finally go over, sometimes it's well out of your control in the sense that you have an older property, and to re-roof it to accommodate solar thermal might be just completely out of whack there. So, but again, if a variance seems to be in order for you, then I'm sure Gail, Eric, Howard, anyone at HSEO would be able to help you find the resources you need to apply for that and consider that heat pump option. Next slide. All right, so this is a recent custom project that I was able to do. It is for the Hawaii Agricultural Resource Center, which is the old Kunia Village the old pineapple plantation. I believe it was Dole Cannery at one point. So Hart took over as far as management. They are offering affordable housing rentals. It is a nonprofit. And of course, there's limitations to whom can apply for that rental. Because of that and what I offer, we were able to do the direct installation of 43 heat pump water heaters at no cost. So it was fully funded by Hawaii Energy. And again, a lot of these were based on what we were able to evaluate when we were on site. Location of the roof, how much sunlight they were getting, so shading, etc. And it's just based on location. So in the event that it is part of the A&A effort, there's potential for a fully funded project. But for the most part, we highly subsidize a lot of these projects that fall into those categories. But for those that don't fall into A&A and it's just your personal home or it's a client's home, we also have market rebates, which we hope you will all apply for. So next slide. All right, so standard residential consumer incentive, you can see here, we try to keep it as simple as possible. So you could go to this link and download the application, fill it out, and we'd be able to provide that $500 rebate. So there is the product finder. So there's various Ream products, A.O. Smith products, and a plethora of others. And so we try to stay on top of those things. But we're always here to answer any questions you might have about them, be it heat pump or solar for that matter. The main thing is just to move away from the electric resistance. Next slide, please. All right, so I know majority of what you've heard today is on basically ducting, air quality, et cetera. So I didn't have as much on that, but I wanted to make sure that I brought a little to the table on it. And so be it a window air conditioning or a tune-up, we also have the central air conditioner and mini split options as far as rebates. So you can see how much more we offer for those options. And I think for existing builds, if you're not doing a standard window unit, which would be pretty quick instant rebate you'd find at Home Depot, Lowe's, etc., then you might be looking at the mini split, which is really the most popular and probably the easiest to implement for existing homes, just based on ducting, etc. So looking at this, I wanted to make sure you had an idea what it would take for the area you might want to replace. And so I've added the unit capacity and SEER ratings along with the rebates to help you look at that. But by far, mini split is the best option if you're looking to upgrade for the long term, which you can see there at 20 plus years. Next slide, please. Okay, and beyond, of course, AC, we do offer solar attic fan incentives. I don't see a whole lot of those from my standpoint and what I do in affordability and accessibility. Whole house fans, I think it really comes down to location and where you're at. Especially if you're west of Oahu, as an example, not necessarily going to be the best option just because of the heat element, but for a lot of other areas, it might be perfect. But again, it has a lot of ducting and things like that. But for those that can take advantage, please do. And then we do have promotions and things we try to do for air purifiers and cleaners. I wanted to gather some information. Of course, you might all be aware of what happened, I believe 2017, 2018 with Big Island, and the geothermal plant went down. So we tried to provide a lot of these types of systems for residents of Hawaii County, just because of the crazy VOG. But one of the most recent efforts we were able to do was for the American Lung Association, which was just a couple of months ago. And you can see the potential savings there. and why we want to push these types of products. And again, this would be part of that hard to reach or accessibility area of what I look at. So next slide. All right, so what is the American Lung Association? This gives you kind of just a basis of what their mission is. Nonprofit, and it's just a great organization. So we were able to provide 50 of these Winex A230s, which is 230 square foot area as far as room purification. And we estimated the lifetime savings on that at 175,000. 725 on the KWH. So cost to ALA was nothing. And that's really my primary focus and what I get to do. But the point is, be it ANA type community or just standard rebates, Hawaii Energy has a lot of options for you. And so if there's ever a question as to if we're trying to upgrade or do anything that has anything to do with energy efficiency, that you reach out to us. So anyhow, I appreciate the time. And if you have any questions, feel free to give me a call.
Thank you very much, Justin.
Absolutely.
I neglected to mention earlier that if you guys have questions, please enter them using the Q&A feature here in Zoom. And we're going to try and get to some of these questions in a minute. So go ahead and enter questions if you've got them for on any of the topics that we've talked about so far. And speaking of topics, this is the last one, lighting. I'm going to give a quick tour of these lighting education modules. There's a lot more information in there than we have time to talk about. So just going to give you a taste of what's there. So on the fundamentals of energy efficient lighting, one question is, why do we care about lighting? The lighting technology has improved a lot in recent years due to advances in LED lighting. And where in a commercial building, lighting perhaps made up 38% of the energy bill, now it's, in this example, down to 17%, but it's still a significant chunk of the overall energy consumption in commercial buildings, especially. So it's important to pay attention to. And the education modules have some information about lighting efficiency strategies. So they talk about 3 elements to efficient lighting. And so the first is illuminance level. So choosing the right amount of light, not too much, not too little for your project. Avoid overlighting a space to save energy. And the appropriate amount of light depends on a number of things like the type of the visual task in the space, the size of things you're looking at, or the contrast of the task. So those are the ranges that you see here, from maybe 10-foot candles up to as much as 100-foot candles in some cases. The other factor implied by the picture there is the age of the observer. So aging people like me need more light. In fact, sometimes as much as twice as much illuminance as young eyes. And when we talk about illuminance level, we often use the term foot candles. So what is a foot candle? So that's the amount of light, which we describe in units of lumens, divided by the square footage of the area being lit. So lumens per square foot is a foot candle. And those were the ranges that you saw in the previous slide. You may also hear about lux. Lux is basically the same thing, except it's lumens per square meter. So when you see lux numbers, they're going to be about 10 times higher than the equivalent foot candle number. And then after illuminance, the second element is lighting source efficacy. So of course, we want to choose efficient sources. These days, it's really LEDs. One point to remember here is that not all LEDs are equal. So it's important to look at the specs on the lumens per watt that you get from different sources. But it's kind of a no-brainer these days to use LEDs over other sources in most contexts. And then the third component is proper controls. So turn the lights off or dim them when they're not needed. So we'll talk a little bit more about controls in a minute. The second module is about lighting power density. So this is the concept that the energy code uses to set upper limits on the amount of lighting power that's allowed. I'm sure a lot of you know that. And these limits are defined as lighting power density or watts per square foot of lighting for different types of spaces. In the building code, there's really two methods. There's the building area method, which is this one. Like, for example, a hospital type building is allowed 1.05 watts per square foot of lighting. And then the second method is the space by space. The calculation takes a little more time. You would have to look at the allowance for each space type in your hospital, for example, and then add up the allowance for all of those spaces. So it takes a little more time, but it might give you a somewhat more generous limit for your project. And then, you'll also, if you've been tracking energy codes, you'll note that with each code cycle, the lighting power density limits get lower and lower. And that's because, technology's been improving. Incandescent lamp might give you 800 lumens for 60 watts of electric input, while an LED will give you 800 lumens for 9 or fewer watts. The efficacy is much higher for LEDs. And then we're still not at the limit for LEDs. There is a theoretical limit for the efficiency of electric lighting sources, but we still have a little ways to go. So we'll probably be improving for a number of years still. Finally, there's lighting controls. So, the most efficient light is the one that's not on. There are a number of different types of controls, and we'll talk about how the energy code deals with it. Now, this is talking about the commercial energy code. For residential buildings, the lighting requirements are pretty simple. We'll get to that in a minute. But for commercial buildings, you need to have occupant controls or automatic timers, and in some cases, daylight controls. I think all of us are pretty familiar with occupancy sensor controls. What we may or may not know is that there are two different technologies that are used. One is called passive infrared and the other is ultrasonic. And there are pros and cons between them. The passive infrared senses heat, like a heat object. And if you move, then it senses the heat's moved, and that means it detects motion. But it needs a line of sight between you and the sensor. Ultrasonic uses the Doppler effect in that it's got a speaker emitting high frequency sound that reflects off you. And if you're moving, there's a slight shift in the frequency, and they have a microphone that receives that reflective sound, and it says, okay, I see a shift in frequency, so somebody's moved. So they both have their pros and cons, and some sensors actually include both. So check out the materials for more on that. These types of sensors are required in a bunch of spaces by the energy code. You see those listed here. When they're not required to have occupant sensors, they're in most cases still required to have an automatic time switch. So you do either occupant sensors, or if not, then you're going to have to use a time switch. And these are required in spaces that are not equipped with occupant sensors. And then there's some exceptions for cases when, usually for safety reasons, you don't want lights shutting off automatically. The last type of lighting control, the third one, is daylighting controls. So these, as I'm sure a lot of you know, use a photosensor to detect the presence of daylight, and it will either dim or turn off the lights when there's enough daylight. So it saves energy during the day. And per the code, sometimes these automatic controls are required in daylit spaces. And there's a definition for what a daylit space is in the code, but basically it's a space near a window that's got a minimum amount of lighting power. And in those cases, then you would have daylit controls or daylighting controls with some exceptions. So that's the super quick tour of daylighting or lighting controls. Lots more information in the modules.
Eric, let me break in with a brief advertisement. A lot of our audience are architects, and if you want to do your clients a favor and go beyond code, just look at the LED sources that are available there. The code maximizes the available lumens per watt as 65, but go into a hardware store and look at LEDs, you cannot get an LED that is below 85 lumens per watt. And most of the LEDs are more like 100 lumens per watt. So specify those, your lighting power density goes way down, your heat gain goes way down. Good way to serve your client very well. Thank you.
Thank you, Howard. Yeah, and so that's a good introduction to our last slide, which is the residential energy code requirements for lighting. So this requires high efficacy lamps and at least 90% of the permanently installed lighting in the space. So LEDs meet that. Fluorescent lights also meet that, but presumably LEDs are going to be the cost-effective choice in most cases these days. All right, so congratulations to you folks who've hung on this long. We're into our wrap up. So we've got 5 minutes or so for some Q&A. I guess, are there questions that I suppose any of the others have noted that we should be trying to address here? I see there were some questions that were addressed online.
Yeah, Eric, you helped me to handle them. One question from one of our best customers is, who represents a very large institution, we are still getting pushback from maintenance about the cost of replacing LED ballasts in new commercial or controlled lighting systems. I'm not understanding the question because LEDs do not require ballasts. Do you have any insight on that?
I'm not sure, so if we're talking about lighting retrofits, you'll remove the lamp. Well, there's different ways to put in LEDs. There are some LEDs designed to work with fluorescent ballasts, which are not the desirable cases. Ideally, you take out the old ballast and you use new LEDs with their own drivers. That's more efficient and more controllable. So I see Brenda noted there are power packs included in a new Lutron system. Yeah, we'll have to get back to you about that specific issue. There are some technical challenges to retrofitting commercial fixtures, and there are a couple different options for the type of approach that you use to putting in LEDs in the place of fluorescents.
Yeah, another consideration here is that Hawaii Energy does offer rebates for when you specify LEDs, so that reduces the upfront cost there. Oh, and here comes Hawaii Energy himself.
Yeah, I just want to, because we do have a number of my colleagues that work in these areas, and I know for a fact we can assist with this. It's just not my personal projects or programs, but you should definitely get in touch with us. So Brenda, if you send me an email or reach out, I'll make sure that you reach the right person to find you that information.
I see there's also a question about 3D printed homes. So what are our thoughts on green 3D printing? I have to say that I haven't been following it too closely, and so I don't really have an educated opinion about 3D printing, except it's pretty cool.
Yeah.
If that helps. Yeah, so Palmer asked, is mean radiant temperature independent of the emissivity and or absorptivity of the surrounding surfaces? Yeah, that's an excellent question. So in last week's webinar, we talked about radiant barriers, which are low E materials. So they have a property, surface property that's low thermal emittance. So even if the surface heats up, it's not going to radiate much energy. So the mean radiant temperature is affected by the thermal emittance of the surface. So like if you, for example, have the opportunity to go up in an attic. So it's like a hot attic, one with a radiant barrier and one without a radiant barrier. If you go up into the hot attic that has the radiant barrier, you will not feel as hot, even though the roof surface is equally warm to the other attic, because it's not radiating as much heat on you. And so your effective mean radiant temperature is lower if you wrap your room in tinfoil, essentially. So there are limits to the materials available that have low thermal emittance, because most materials have a fairly high, say 0.8 to 1. But
And
yeah, if you're
Eric,
able to develop a ceiling surface with low thermal emittance, that'll also help you feel more comfortable.
Eric, we had another question about CO2 levels. First part of the question, is CO2 a good metric for measuring overall IAQ? And number two, does any code put a maximum number on the amount of CO2 allowable in a space?
Yeah, so that's a good question. Yeah, so CO2 is a good proxy for the number of people in the space, because we sort of emit known levels of CO2. So if the occupants are the main source of pollutants in your space, then CO2 is a good indicator. But it doesn't capture a lot of other potential problems, like, somebody just cleaned the floor with bleach, and so there's that kind of problem, or the materials are off-gassing formaldehyde. So it's only a part of the problem. As far as maximum allowable CO2 levels, not directly, I don't think. The ventilation standards, I could be wrong about that. The ventilation standards are kind of based on maintaining appropriate CO2 levels, but yeah, I'm not sure. I don't think there's a maximum limit in the code. We are kind of at the end. I think appreciate the questions. I want to give time for Justin to come back and get to the most important part of today's presentation, the awarding of the Zippy's gift cards. Justin?
Oh, yeah. Yeah, I get a big privilege here. So this is awesome. So Karen was out today. She asked me to do this, and Howard was nice enough to let me know that you were only looking at the top of my head for the presentation. So I apologize for that. But anyhow, we do have a few winners, and it looks like the first one is Clarence, and I apologize if I butchered the last name, Clarence Nkube. The next winner is Albert Torres, and our third winner is Mary Rixey. So for those of you that have stuck around, we will email you to establish some contact, and then we'll figure out how to mail you your gift cards to Zippy's. So thank you, everybody, for being here. We appreciate it.
And let me point out that Clarence is the super duper energy supervisor of HPU, Hawaii Pacific University. So good, good deserving there.
So Clarence, you had your hand up. Did you have a specific question?
I think he's saying present.
Okay.
Okay. Yeah. We know you're present, Clarence. Yeah.
Maybe,
Well,
maybe. I don't know. Let us know, Clarence. Yeah.
Okay. Well, that does it for webinar number 2. If there are more questions, please email one of us. And if we're not the proper person, we will get to the proper person and get to you. This is a very important seminar, great potential for moving closer to a decarbonized Hawaiian economy. And on that very cheery note, we say fond adieu, aloha, and see you next week for Zero Net Energy webinar number 3. Bye-bye.
Thanks, guys.
Please answer. We have a feedback summary. Please fill that out before you leave.